I want to now just compare a couple of ways that we can represent the movement of this particle graphically. Now, the most common thing we'll see is that we would graph position as a function of time. So we would have time measured in seconds on the horizontal axis, and position as a function of time, which is measured in meters, on the vertical axis. Now, I've purposely not drawn the negative t axis because for this problem, we're not concerned with negative time. Okay. For most application problems, we won't be concerned with negative time. Whenever we start measuring things, we'll declare that to be time zero and just look forward. In theory, though, I could have something where I am concerned with negative time. If I'm saying, okay, I'm going to declare time zero to be Monday, but I'm looking at what happened on Sunday, that would be at a negative time. So it could occur. We just arbitrarily choose some time to be zero. Usually we choose that to be our starting time. Position, we've said, is a signed quantity, so I'm allowing it to be either positive or negative. Now, I'm concerned here with the time interval from 0 to 4. And if I were to graph this, I actually know what this looks like. This is just a parabola that opens up, and its vertex is at the point 2, 0. Okay. And at time 0, my position is 4. And at time 4, my position is 4. Now, graphically, I can see several things that we've already learned. I end and I start at the same position so that my displacement was 0. I can see the graph started out going down. Over the first 2 seconds, we were going down, so velocity was negative. Over the next 2 seconds, we were going up, so velocity was positive. Okay, and I can even calculate my distance using this graph, because I can say over that first 2 seconds, we went from a position of 4 to a position of 0. Position is what I'm putting on the vertical axis. So we traveled 4 meters. We just went in the negative direction. And then we went from a position of 0 to a position of 4, so we traveled another 4 meters. Okay, this is the standard way that we graph these things. One problem with that is that moving to the right along this graph doesn't have any physical meaning. That's time passing. So this sort of suggests that the object is moving down and right and up and right, but it's not. Remember, the object was just moving left and right. We said we were looking at a particle that was moving along a number line. So if this is position 0, 1, 2, 3, 4. So this is our home position, okay? We actually started at position 0. Let me just get a different color here. Sorry, we started at time 0, we started at position 4, okay? Here's what the particle actually did. It went to the left, and then it went to the right. There was no up and down there. It was just horizontal movement. That is not a way I'm going to represent this graph, because this now has no connection whatsoever with time. All I can see from this is that at some point I was at all of these positions that I've shaded in red. This picture is utterly useless, but yet that's what actually happened. The particle started here, it went here, and it came back. Okay. So what I'd like to try to do is to get something that resembles a little bit more what the particle did. Went over here, turned around, and came back, that doesn't have this same two-dimensional nature to it. Okay. So here's what I'm going to do. I'm going to put a position axis right here. But I'm not going to actually draw the particle's position on this axis, because when I do, when the particle turns around to come back, it just overlaps itself and it's really hard to read. I know that at time 0, we started at position 4. So I'm just going to mark a starting point directly above position 4, and I'm just going to make a note that that's when the time is equal to 0. So instead of giving time its own axis to turn this into a two-dimensional picture, I'm just going to indicate it by labeling things. Okay. Then, over the first 2 seconds, we traveled to the left. Okay. So I want to indicate that we're going to travel to the left until, at time 2, we're at position 0, which I'm going to mark as being above here. Okay. Now, if I'm not careful, I'm going to just repeat this picture over here, just a little bit above this position axis, and that's not going to be particularly helpful. So let's think of an analogy. Let's suppose that we're driving on a road, and we drove for a while, and then we said, oh, I forgot my wallet, I've got to turn back and go home. So we're going to turn around and we're going to go back. Now, I'm sorry if that has ever happened to you, but it probably has. I very much hope that when it did, and you turned around to drive back, you didn't drive in the same lane. I hope that you changed lanes so that you were always driving on the right side of the street and didn't cause a car accident. Okay? So that's what I'm going to do here. We're going to say over the first 2 seconds, we came to a position of 0, and this is where we were at time t equals 2. And then we traveled back to our position, the same starting position at time 4, at position 4, which is where we were at time 4. So I have introduced a vertical component here, but I can still see visually. I just went to the left and then went to the right. I still sort of see that one-dimensional motion. This is just like changing lanes. It's just going up just enough so that my trip going to the left doesn't overlap with my trip going to the right. Okay? So this sort of preserves that I can see visually, yeah, I was just going left and then I was going right. And it looks more like what the particle actually did. It went to the left and then it went to the right. Whereas here, there are two things going on. First of all, we've put position on the vertical axis, so we've translated horizontal position into something that we're representing vertically. Perfectly acceptable to do, but it means that my perception is a little bit different. But more importantly, we introduced a physical dimension for time, and time isn't a physical dimension. So they both accurately represent what the particle was doing, but this more directly matches a picture of what we would see if we were watching the particle. You will see in the homework, or in the text, there's a picture that's called figure 2 that looks something like this. So I'm just going to say this is like figure 2 in the text. So some of the homework says draw a diagram like that in figure 2, and that's what you're being asked to do. Now on an exam or quiz, I can't really say draw a diagram like figure 2 because I don't expect you to remember figure 2. But if I ask you to do this, I would ask you to say draw a diagram similar to what you did in the homework where you're representing position just horizontally, like so. So find some way of describing this. You could be asked to do this. If I give this to you on a take-home quiz, I'd probably say draw something like figure 2, and then of course you're allowed to refer to your textbook.